Let us start this lecture with a thought process by great Saint Swami Vivekananda, who says, "Men, men, these are wanted. Everything else will be ready, but strong, vigorous, believing young men, sincere to the backbone are wanted." Still we are waiting for human being or for men of the caliber of Swami Vivekananda who can really build the modern nation. I wish and hope some of you will come to that label, so that our country can be rebuilt. Let us recall what we learnt in the last lecture. In the last lecture, we basically classify the solid propellant grain into 4 types, and then we discuss about at length. And later on also we learnt how a solid propellant grain can evolve during the regression of it. And we have learnt about Pivot law, and also we have applied, considering example of a square safe grain, 2-dimensional grain. And also we looked at how to calculate the sliver, how this surface area and the volume is changing, and what will be the things and like that. And today we will be looking at basically burning stability. And whenever we talk about the burning stability, basically we looked at how this pressure changes with respect to time. Let us consider a radial burning grain. In this case, as I told earlier, the regression will be taking place in the radial direction. If I consider this as a axial direction and this is your radial, so also other surfaces. And this front, regression front will be moving, and then as I told earlier that the propellant surface will be regressing layer by layer, and mass will be generated into gases, and as a result there will be increase in the chamber pressure, provided that all the mass is not passing through this nozzle area. This is your nozzle area A n, and throat area, and I can say this is basically A t is the throat area, and there will be some mass flow rate which will be passing through that is known as nozzle mass flow rate, and some mass flow rate will be passing to this gas. And we have already seen that related this mass generation of the gas and also the mass flow rate through the throat of the nozzle. And when you do that, we get a relationship that rate of change of chamber pressure will be basically related to, this is your amount of gas being generated, this is G, and this is your mass flow rate through the nozzle. And if there is a difference between that and that will be accumulated, and there will be pressure increase, and if there is a less than the, if it is m dot g is less than the f dot n, then the chamber pressure will decrease. So, let us consider that a case where the pressure index, and this is your pressure index, or sometimes we call also the combustion index. When n is greater than 1, the curves will be like that, and whereas this is corresponding to the gas generation rate, this is m g, and nozzle flow rate we call it as a m n. So, m n will be linear because this is governed by m dot g, as I told, it is basically p c power to the n. So, therefore, it will be depending on the pressure very much, and whereas m dot n is linearly proportional to chamber pressure if you keep everything remain constant, like T c is constant, A t is constant, like that. And when this is the operating condition, what it would be? If you look at, this is your operating conditions, that means there will not be any change in the pressure. right, and it will be balanced. That means, m dot G is equal to m dot C, and you are having certain pressure. If there is a increase in pressure, let us say it will increase by, let us say it will go to in this point. If it is if I say this is P C 1 and this is your P C 2 and P C 2 is greater than P C 1, then what will happen, that the mass generation rate, in this case the mass generation rate, that is m dot G, is greater than the m dot n. If it is greater, then what will happen, the chamber pressure will go increase further. That means, it will get into another one. So, that and then the difference between this and 2 are increasing. So, this has increased. So, therefore, this again there will be increase in pressure. That means, if there is a little bit perturbation to this operating point, this is known as operating point, then it will be goes on increasing. If you go other way around, if I move to here this side, this is, let us say this is P C 2 dash and P C 2 dash is less than the P C 1, this is the one. So, therefore, in this case what will happen, like you are operating at this point. So, the m dot n is higher as compared to the m dot G. So, if it is less, then what will happen, that the chamber pressure will decrease further. That means, the point will be shifting towards again this another one, that is your, let us say P C 3 dash. So, it will goes on shifting toward that. That means, if there is a perturbation under this condition, either increase in pressure, chamber pressure, or decrease in chamber pressure, it will be drifted away from the operating point. That means, imbalance will be there. So, therefore, it become unstable. So, let us consider a case that where n is less than 1. So, if I consider S is less than 1, so this is again my operating point, and if there is a increase in pressure, let us say here with corresponding to let us say this is P C 2, and then in this case P C 2 is greater than P C 1. In this case, what is happening? This is just opposite is happening, that is m dot G is basically is less than the m dot n. In other words, in this condition is m dot n greater than m dot G. So, that means pressure will be reduced because the accumulation of mass is reduced. So, pressure will be coming back to this point, and if you go to the other way around, that means the chamber pressure is decreases, let us say by certain amount, then what will happen in this case, that the mass m dot G is greater than m dot n in this point. So, if it is so, then what will happen, that chamber pressure will increase because the accumulation will be higher, will increase. If accumulation of mass will be increasing, then the pressure will be coming back to this, that means to this operating point, and as a result what will happen, this is the stable operation. That means, the pressure index must be less than 1, and we have already seen that for stable operation the n is varies between 0.3 to 0.8, which is less than 1, and keep in mind that generally this is corresponding to the double base propellant, and then lower values to the composite propellant. and composite propellant are more stable as compared to the double base propellant. So, let us look at how does the chamber pressure vary to the propellant grain temperature. Earlier we have seen that how this regression rate will be sensitive to the propellant grain temperature, and we can define in the similar way, that is of course considering the chamber pressure derivation what we have done, and keep in mind that this ratio will be keeping it as a constant, that is A b by A t. This is constant. We are keeping also chamber temperature is remaining constant. So, we can say that sigma p, that is the sensitive of chamber pressure to the propellant grain temperature, is equal to 1 over chamber pressure P c and d P c by d t, and where the A r and T c are constant. So, if you look at that, I can find out that this is, if it is constant, then naturally P c will be k is your constant into A is your basically it is a temperature coefficient, you can say, because we know A is equal to A by T I minus T p, and A, this is a constant, but of course, the T p will be changing, and this k is a constant, and A power to the 1 divided by 1 minus n. So, therefore, we can write down this differentiate, we can say that this k A 1 divided by 1 minus n is equal to d k A 1 divided by 1 minus n, and d T p A r and T c is constant. So, if you look at that, we can say this is sigma p is basically that is, I can take this k, and this is k A 1 divided by 1 minus n into I can say this is basically, that is A, I have taken this, and then if you look at this is equal to A 1 minus n minus 1 into I can say this is basically 1 minus n into d A by d T p. Keep in mind that this I can write down as, basically this I can write down as A 1 by 1 minus n into 1 by A. So, this will cancel it out, k will cancel it out. So, I will get basically 1 divided by 1 minus n and 1 by A d A by d T p. Keep in mind that this is nothing but your sigma r dot, that already we have derived. So, therefore, you will get sigma p is equal to 1 divided by 1 minus n sigma r dot, and it can be seen that this sigma p is greater than the sigma r, because n is less than 1, and keep in mind that n should not be very close to 1. If it is very close to 1, then this will be very high value, that means the chamber pressure will be increasing at a rapid rate. So, even if little bit change in the T p. So, therefore, it is important to keep this n as closer to or closer to the lower values, so that this sensitiveness will be lower down, and so that it will not lead to explosion due to some kind of grain temperature, which may be varying because of various reasons. And let us conclude that hence the sensitivity of the chamber pressure to grain temperature is greater as compared to the sensitive regression rate to the propellant grain temperature. And of course, if there is a increase in this AB surface due to the any reasons of fracture or the crack in the propellant, and chamber pressure also will increase. So, and beside this we have already seen that the chamber temperature how it is changing, and with respect to regression time. Let us consider neutral bonding grain, which is at 15 degrees Celsius. When the temperature is increasing, there is an increase in chamber pressure, so also the thrust time. But however, the burning duration, that is your duration of burning, that is Tb, I can say it is also getting reduced with increase in the propellant temperature. Let us look at ignition system, which is very important for initiation of combustion. So, if you look at what is the function of an ignition system in solid propellant rocket engine, you can really say that the function of an igniter is to initiate the combustion in a solid propellant rocket engine, such that a smooth combustion in specific time interval can possible without really occurrence of any undesirable pressure spikes. Sometimes you may provide little higher amount of energy to save time or to have a quick ignition, but however, it may lead to the very high chamber pressure leading to explosion or leading to the failure of the engines. A typical ignition system has two major components, namely initiator and other is energy release system. That means, one has to really initiate the combustion. How one can do that is also one question. It can be reliable, it can be repeatable, such that you can have, and we will see how really we can initiate the things. And then there should be also a system which can give you the sustainable amount of energy, such that complete ignition can take place over the entire surface of the propellant grain. And the function of initiator, as I told earlier, is to transfer thermal energy from electrical, mechanical, optical or even high power laser to the main charge for ignition to take place. And in an initiator, safety system must be introduced depending on the mission requirement, because it is very important. Otherwise, it may happen that you are having propellant, and then in the combustion chamber it may ignite even with little bit jerk, or maybe some kind of a shock wave or some other energy sources which will be there due to maybe electromagnetic waves and other things. So, one has to be very carefully design this, and several types of initiators have been designed and developed for reliable and safe ignition of solid propellant engines, and we will be discussing some of them only, and some of these initial stimuli, because the initiator will be giving basically initial stimuli for ignition, can be provided by several kinds of bridges or the initial energy, that is electrical resistance, semiconductors, as I mentioned, lasers, lights, or the mechanical, maybe some pressure or shock waves or any other things which can be used for giving stimulus or the initial energy for ignition. And the most widely used initiation system is the electrical initiator, or which is also known as a squib. Squib is basically a fire path which will be given by the electrical current, such that it can initiate the combustion with a hissing sound before it is exploded out. So, this can be either a hot wire which will be kept in a propellant, and that is sensitive to the heat energy, and or can be an exploding breezeware can be used, which will be coated with the propellants. Whenever the heat will be going, that heat will be generated due to the passing of current in the wire, so that it can really ignite, or the combustion or the chemical reaction can be initiated in the. So, let us look at the solid propellant igniter. There are various types have been developed igniting the solid propellant. It can be broadly divided in two types. One is pyrotechnic igniter, other is pyrogen igniter. And in case of pyrotechnic is basically the propellants which is being used, and then that will be helping in directly initiating the combustion on the surface of the propellant grain. And generally the black powder which is being used as a pyrotechnic material. Apart from that, you can have also some metal powders and propellants are being used. The black powder, as I told earlier, 74% is potassium nitrate, 15.6 carbon and 10.4 sulfur are being used. Apart from this, like some metal powder can be added as well. So, if we use this black powder, the product will be containing 40% gas and 60% solids, but it may vary, and if it is this is the proportion, then the ignition temperature what it can achieve is 2590 kelvins, which will be good enough to initiate the combustion in case of solid propellant. There will be also pyrotechnic propellant, which is a mixture of metal like aluminum, magnesium, boron, and of course, the potassium perchlorate, potassium nitrate and other oxidizers along with the binders, and which will be used. And also there might be some burning rate enhancers which can be added to that. Let us look at a basket type pyrotechnic igniters, and if you can look at this electrical leads which will be having, and whenever this current will be passing through that, and this resistance, this is your resistance, when the current will passing through this resistance, it will be generating some amount of heat. And this is generally the nichrome wire of a smaller diameter, around 0.1 mm is being used, and this current whatever it will be flowing is also no fire, that means there will not be any fire, even with small current will be passing through it, and there will be also the all fire, that means if certain threshold amount will be supplied or more than that, then the fire will be occurring. That means reliability will be there, and so also safety. The difference between no fire and all fire currents are much higher generally, so that the safety being taken care, there is some standard which is being used. And these electrical wire are being coated with the some kind of chemicals which are sensitive to the heat. So that the reaction can take, like lead azide, and also the mercuric fulminate and some other things. And whenever it will be there, these are very powders propellant which will be there, and heat will be passing through that nearby, and then it will be igniting, and this is generally the high burning rate propellant is being used, and so that will be acting like a booster. And this has been sealed with a casing. It can be malleable metal, it can be also like a plastic or made of polymer or some other cellulose kind of materials, and with certain holes. So, whenever this will be that some holes will be created, and then the gases will be passing through that this gas and hot gas, and this will be getting into this kind of pyrotechnic mixture with certain sizes, and it will be ignited, and then some combustion heat will be released, and some particulate will be going. So, it will burst it out various ranges, and then the propellant surface will come in contact with this hot gas and the solid particulate which is being used in the pyrotechnic propellant, and this is known as basically the relay propellant because it is moving, and this is a booster. And this basket type pyrotechnic igniter is used for smaller size rocket engines. For medium size rocket engine, this may not be good enough. Therefore, people have come up with a jet pyrotechnic igniters. And if you look at, this is similar to that, this is also known as squib, we call, and this booster is similar to that. Whatever I have explained here is having electrical current will be passing through this resistance, and then this will be initiated, and then gases will be getting into, and it will be pellet, main charge will be having pellet. These are all particulates, maybe in micron size, these are particulates. In case of pyrotechnic, these are a bigger size, the gas can be flowing through that, and it will be ejected with a velocity of very high temperature gas, and along with some particles. So, some particulate will be also going through, maybe small particulates will be going through that, and that will be ignited. And these are two kinds of pyrotechnic igniter. You can design various other kinds as well depending on your requirement, and pyrogen igniter is used for a bigger engine, and this itself is a rocket engine, small rocket gas generator, which will be producing the particulate. If you look at, this is having a small pyrotechnic igniter. So, this is, you can consider this itself is a pyrotechnic igniter. But this is having a pyrogen igniters, and this is a these are the propellants, these are propellant. And when this will be coming, this particulate will be coming over here and then hitting this portion, and then it will be ignited, and this portion will flame. For example, some particle will be coming over here and some ignited into particle, and then that will be, the flame will be formed. This flame will be formed, and it may, the flame may be formed over the entire surface. These are the all flame to start with, and then after some time this flame will be mixed together kind of things, and then the entire surface of the propellant grain, this is your propellant grain, will be there, and the entire flame, and this flame is covering entire surface of it, then only ignition will start. So, therefore, pyrogen igniter will be containing also the pyrotechnic igniter to be, and this itself is a small rocket gas generator which will be generating gas, and so that, and this is used basically for a bigger size rocket engines, and generally for your space launch vehicles this pyrogen igniters are being used, whereas for smaller rockets the pyrotechnic igniters are being used. And let us look at ignition process. As I told earlier, the ignition is basically will be taking place, there will be some kind of initial inert heating, and this is your igniters which will passing, as I told, and then a flame sprayed over will be taking place here. This is known as flame sprayed over, sprayed over, and then only the ignition will start. In initially the pressure will not be really changing much, and if you consider the chamber pressure versus time, and let us as I told, there will be induction phase. This particulate will go and impinge into this propellant grain, and then this smaller flame will be taking place, and then after that, of course, flame spreading will be taking place. There will be some kind of a entire regions, and the whole entire the propellant grain will be taking place, and this is known as flame spreading. After that, of course, there will be increase in pressure, and then if it is increasing, this is known as chamber filling. This region is known as chamber filling, and of course, after that if it is a low AP by T, the port area, this is your port area, and this is your throat area. If it is a, that means the gas velocity will be very high Vg, and such that there will be erosive burning. After that, it will be coming back and then attaining the steady state values. Of course, for the high APT, the induction phase, the initial heating is very high and the pressure will be picking up, and then again it will be, and it is not the high APAT is not experiencing erosive burning. And keep in mind that one has to be very little careful about how much ignition energy one has to give. So, if you give certain amount of ignition energy such that it will be all this energy will be trying to heat this solid propellant. However, a lot of heat will be getting conducted into the surface such that it cannot sustain the combustion, it will be coming down, that is corresponding to A. But if you give much little higher energy than that, then what will happen? Of course, it may lead to a very high ignition energy, and then high chamber pressure will be there, and then of course, it will be experiencing the erosive burning, and it can come back after some time once this port area increases further, and then it can come to a steady state. But if you give a appropriate one such that it will be ignited slowly and steadily, it will be reaching the steady state pressure Pc. So, then it is known as normal ignition, the D is basically normal ignition. And if you give a very small amount of ignition energy, then what will happen? There will be certain kind of chamber pressure increase, but it may not really sustain because the amount of heat release during this initial phase of combustion of solid propellant is not good enough to sustain the pressure. As a result, the pressure will be going down, and then it may remain for lull for some time. Then again there will be some reactions, there will be accumulation product, again it will go up, and this is known as hang fire. So, therefore, one has to be very careful about this ignition energy amount and also the duration, which is very important. Generally, the duration is also very important for initiation of combustion. You should have very as less as possible, and of course, smaller rocket engine can have something around maybe 50 milliseconds or to 60 milliseconds, whereas larger rocket engine can have a higher one. Let us look at how this chamber pressure will be changing with respect to time for the entire region. As I told, there will be induction or the inert heating, and this is known as ignition delay, because this is portion, in this case we can call it as a ignition delay TD, this one. That means, there is no appreciable change in the pressure in the beginning, and this will be around 10% of ignition pressure when it is we define this ignition delay time, and then there will be increase in pressure because there will be flame spreading over it, and then will be going up, and if it is a erosive burning, then pressure can go beyond this steady state value. This is your steady state value, steady state Pc, and it will go up, and then again it will go, reduce down, and this time is known as basically ignition time, that is corresponding to 90% of Pa ignition pressure. Generally, this ignition pressure will be quite little bit 70 to 80% of the chamber pressure what you can have. And of course, in this case it is the peak pressure what it would be, and in this example what we are considering, and then of course, it will be receding and it will reduce whenever the propellant, most of the propellant burnt out, only sliver mass is there, then it started receding and reduce because of sliver mass getting burnt out, and then it will go down, and then after that it will be reducing very much and it will be useless. So, therefore, this C is corresponding to basically the burning time, the burning entire time, because this is your started over here and this is the TB is the burning time, and actual action time will be taking from 10% ignition pressure corresponding this chamber pressure time diagram, and this is your action time. After that it is having no value and it cannot really give any thrust as such. So, therefore, one can define from the chamber pressure and the time history and various times and on as to look at what will be the way of enhancing the action time and also the burning time. So, let us look at about like what is the minimum amount of charge for successful ignition. If you look at that, we can get that basically mass is we can find out this will be greater than equal to the rho of the gas into the Vc, and using this because the chamber volume has to be filled such that the pressure can build up, and keep in mind that by using ideal gas law, we can find that rho g is basically P. If you look at this is basically P by RU T molecular weight. So, if I can find out that is become basically m dot ignition will be greater than equal to P by this will be chamber pressure or ignition pressure, I can say RU, and this is TIG molecular weight of the propellant, I can say at ignition into Vc. So, this is the from this formula one can calculate what it would be, and depending on the whatever the ignition pressure, as I told, generally the ignition pressure will be basically the something 40 to 50% of the thing what is being taken. So, beside this what we will have to do, we will have to use this thing, some amount of solid particle will be there. So, therefore, I can have this is 1 minus SF P ignition MW ignition and Vc divided by RU and Tc or T ignition. So, this is the expression what you can use, where SF is the fraction of solid material in charge and Pc is your or PCIG that is the chamber pressure at ignition, which is something around maybe 40 to 50% of the steady state pressure, and Vc is the free chamber pressure that include the conversion portion of the CD nozzle. So, that is the important point one has to look at it. So, let us now look at the difference between pyrotechnic versus the pyrogen igniter. And main charge, as I told, the pyrotechnic propellant, whereas the pyrogen will be fast burning propellant is being used, and pyrotechnic can be have powders and pellets. Generally it is being used as a pellets, and pyrogen is a cast as a grain, that is pyrogen. Action time is generally 100 to 200 millisecond, and in the pyrogen longer burn time something 250 to 1000 milliseconds, and the pyrotechnic igniter is used in small solid propellant rocket engine and also the medium solid propellant engine. For larger solid propellant engine the pyrogen is being used. And if you look at relative merits and demerits, the pyrotechnic performance is moderately controllable. Thrust load depends on the test chamber volume, and the pyrotechnic is simple construction and easy to manufacture, and it is quite cheaper as compared to the pyrogen igniter, whereas the pyrogen igniter is quite complex in construction processing, and performance of the pyrogen igniter is quite closely controllable. Therefore, it is being used for a larger rocket engines or the space launch vehicles and bigger one. So, with this we will stop over here, and we have now come to an end about the discussion on the solid propellant rocket engine, and we will be taking off later on about the liquid propellant rocket engine. Thank you very much.